So, this is active filter design lecture 24. In the last class, we saw that the effect of a parasitic pole in a transconductor implies that the response of the filter is no longer what you intended it to be, but something different, and can be found by evaluating not h of s on the j omega axis, but h of s on a contour j omega minus omega square by omega p. So, the transfer function remains the same. It is only that you are evaluating this transfer function now on some curved path, right, which is j omega x minus omega square by omega p, and if omega p is too low, we found that the curved path will eventually, as you bring omega p lower and lower, we saw that the curved path will hit the poles of the filter, at which point the modified transfer function will blow up, which is equivalent to saying that the non-ideal transfer function has poles on the j omega axis. Okay. Now, let us go, now since we have found this intuition, let us see if we can also understand finite gain of the transconductors, right. So, yes, people. Any questions? Okay. Now, let me cover a couple of miscellaneous points before we move on to the next topic. Alright. So, this is the schematic of a second order filter network that we derived from a passive RLC prototype, and this can be also interpreted in another way. If you consider this block, please notice carefully. Alright, I hope the shaded portion is visible. What kind of animal is this? Alright. So, this is the generic form, a transconductor pushing current into a capacitor. Now, if I look at the voltage transfer function VA and VB, VB of S by VA of S is what? G by SC. So, what kind of mathematical operation is this performing? This is an integrator. So, this is what is called a transconductor capacitor or a GMC integrator. Okay. Similarly, what do you see if I now looked at this animal? What kind of animal is this? Well, okay. In other words, this also can be thought of as a transconductor pushing current into a capacitor in parallel with a resistor. In this particular case, that resistor also happens to be a 1 by G. Okay. All right. And this is VA and VB. So if G tends to 0, this will become an, I'm sorry, if I'm sorry, which what I meant was, if this G tends to 0, then that resistor will become infinite, and therefore this will look like an integrator. Now the process of adding the resistor to the integrator basically causes it no longer to be an integrator, and this is often what is called a, I mean, as you said, it's a first order filter, often it's also called a damped integrator. Okay. You understand? And I mean, if this G, if this damping transconductor was 0, then this would also become a integrator. But what kind of integrator? Inverting or non-inverting? What kind of damped integrator is this? Inverting or non-inverting? Inverting. Okay. And what do we see here? If you wanted to draw, a block diagram of the structure, what do you think this would look like? VBP is being integrated to give VLP. Okay, all right. And what else is happening? And what is happening here? Please note that the sum of VLP and the input, what is happening here? The three currents coming together and passing through C1. What are they? One is the input current, one is the low pass current converted into a, low pass voltage converted into a current. Then what else? What is this? This is the band pass voltage converted into a current. All when integrated will give you the band pass voltage. So if you think about it, it is nothing but the band pass voltage converted into a current. Okay, or in other words, the sum. See, please note what is happening here is that voltages are being converted into currents and being summed. Okay, summing currents is very easy, you just need to join the wires and integrate it. Okay, so in other words, you can think of this node as being a summing integrator, where it is integrating not just one voltage, correct, but it is integrating this voltage, a linear combination of VI, VLP and VBP, right. The sign of VBP or the weights of VBP and VLP are negative, okay, whereas VI is positive. So one can, if you wanted to draw a block diagram of this whole operation, you have a second integrator, okay, okay. VI minus VLP alright, and what else? Minus VBP and this is being integrated to give you VB. Alright. So, if the transconductors were different, all that would happen would be each of these branches would have different weights, that is all. Okay. But the key point to notice is that the basic pole forming section consists of two integrators in a loop. Okay. Alright. So, often all these biquad sections are often called double integrator. Loops. And why do you think this branch is necessary? If that branch was not there, what do you think will happen? There will not be any damping, which means that the poles will be on the j omega axis. Okay. So, this branch is necessary, or what it does is introduce damping into the loop and pushes the poles into the left half S plane, depending on how much Q you need for the denominator. Alright. And you can go and do the math and show that if this weight is 1 by Q, alright, and this is omega naught by S, which is, and this is also omega naught by S, then you can show that the denominator will be the form S square by omega naught square plus S by omega naught Q plus 1. Okay. This also gives us intuition about why things start to become unstable when transconductors have internal poles. Right. Yesterday we saw that if every transconductor is associated with an internal pole at omega p, then if the omega p becomes too low, what do you think happens to the Q? Q will be enhanced, and if omega p becomes too small, then we saw that the non-ideal, due to this parasitic pole, the non-ideal filter can have poles on the j omega axis, which is equivalent to saying it's becoming unstable, right? And why does that make intuitive sense? Can you look at this, stare at this diagram and tell me? No. This is fixed. Please note that this is fixed. When you have non-idealities in the integrator, what do you think happens? This 1 by S is going to become 1 by S times 1 plus S by omega p. Correct? So you can see that, I mean, you can understand in many ways, at a very crude level, you can say that there is increased delay, there is this feedback loop here, and there is increased delay. Okay. Or if you like to do this loop gain kind of analysis, then you can break the loop here, right? And adding extra poles, a pole here and a pole here, is equivalent to the loop having a reduced phase margin because of the extra phase lag introduced by the poles. Okay. And therefore the phase margin reduces, which is equivalent to saying that the poles have become closer to the j omega axis. Which poles? The open loop poles or the closed loop poles? The closed loop poles have become closer to the j omega axis, which is equivalent to saying that the quality factor of the poles has increased. Okay. So the one final minor point that I wish to make is that for an ideal integrator, the transfer function is of the form Gm by Sc, and more precisely, what is the angle of the integrator? Is minus 90 degrees at all frequencies. Correct? Now, if the integrator had a parasitic pole, the transfer function is of the form Gm by Sc times 1 plus S by omega p. Correct? So, and what did we say was when we say omega p has to be far away, correct? I mean, what is the meaning of far away? No, yesterday we said that respect the passband edge is only very crude estimate. We said that our notion of far away must be not related to omega naught or simply q, but to the omega q products. Omega p must be much larger than 2q times omega naught. Okay. Now let's see if we can understand this criterion which we derived in a different manner from the behavior of, I mean, obviously the GM having an extra pole must be doing something bad to the integrator, correct? So that when you put multiple integrators in a loop, the loop becomes, or it has tends to become unstable. So what can you what do you think is the phase of this integrator? I mean, the so-called integrator. The phase of this integrator is no longer 90 degrees, but minus 90 minus tan inverse omega by omega. Okay, and if you assume that Gm by C is omega naught, right? Because we just saw in the previous diagram that if you have two integrators with unity gain frequencies at omega naught and you close the loop around them and add a damping path, the natural frequency of the resulting section is Gm by C, which is omega naught. Then and if omega p is much larger than omega naught, then the angle of the integrator, okay, I am putting this integrator in quotes because this is no longer technically this is not an ideal integrator, right? There is some small amount of delay in the integrator, but let's just stick to this terminology. The angle of the integrator is minus 90 degrees or minus pi by 2 radians minus the integrator. Let me just angle of the integrator, let me just do this at omega naught, okay, is minus pi by 2 minus omega naught by omega. Okay, all right. And what is omega naught roughly? Omega naught is roughly Gm by C, and what is, I mean, is there a more physical interpretation to omega naught? Omega naught, which is Gm by C, is also approximately the frequency at which the magnitude of the integrator is what? Is 1. Correct? Why is this justified? Omega p is much larger than omega naught, right? So at omega naught, you can simply, to find the magnitude response, you can simply neglect this 1 plus s by omega p, and that gives the. So the excess, so this quantity, ideally the phase of the integrator was supposed to be minus pi by 2. Now the actual phase is greater than minus pi by 2, right? So this quantity minus omega naught by omega p in radians, okay, is called the integrator excess phase, okay, and can you compare, rather this, the absolute value of this is called integrator excess phase, okay. And we know that omega naught by omega p must be much smaller than 1 by all right. So you can I mean 1 by 2q is basically the phase margin of the loop to begin with, right, and I mean the excess phase introduced by each integrator must be much smaller than the phase margin. That's all that this is saying, okay. You understand? So when you read filter papers, you know, you will often find people talking about excess phase. The reason for this is the following. I mean, as we have seen, the building blocks of all these filters are basically integrators, correct? In our course so far, we have seen only transconductor capacitor integrators, but other types of integrators exist. And once you have a basic building block, which is an integrator where the input and output dimensions are the same, you can put integrators in various configurations and realize arbitrary transfer functions. And in every case, the steps are the same. You know the transfer function, you come up with a network, then you dynamic range scale the network, and that will kind of maximize dynamic range, and you're done. Okay. So the building block is an integrator. So whenever you're designing a filter, the first thing you will do is design an integrator and see how good or bad it is. Okay. As we have seen before, if the integrator has got finite gain, for example, what will be the transfer function? What is the transfer function here? VO by VI is nothing but GM RO by 1 plus SC RO, correct? And whereas ideally it should have been, which is equivalent to saying GM divided by SC plus 1 by RO, correct, which is equivalent to saying it is 1 by SC by GM plus 1 by GM RO, correct. If I denote GM RO by A DC, the DC gain of the integrator is ideally supposed to be infinite, but now it is what? GM RO. So earlier for the ideal integrator, you were your integrator transfer function was SC by GM. Now it is 1 by SC by GM plus 1 by A. So equivalently, what is happening? to find the effect of finite gain on the transfer function, what are we doing? If every integrator becomes, instead of having SC by GM, if you have SC by GM plus 1 by A, what do you think will happen? Yeah, that's true, but what do you think will happen to the transfer function? Earlier you had H of S, right? And now what is happening? Instead of S C by GM, you have SC by GM plus 1 by A, which is equivalent to evaluating H of S at S plus, I mean, to earlier, ideally evaluate H of S at S is equal to j omega. Okay. To find the effect of finite gain, what would you do? Now evaluate H of S at j omega plus gm by Ca. Correct? All right. So now, so in other words, in the ideal case, you were evaluating, I mean, these are the poles of the filter, for example, and you were evaluating the transfer function along the j omega axis, right? Again, if you go back to the 3D plot, you are slicing it on the j omega axis, and that cross section gives you the filter response. Now what are you doing? Shift it where? Left or right? What is A? Is it positive or negative? Positive. Okay. Gm by C, positive. So now when the stuff is non-ideal with finite gain, all that you have to do is evaluate H of S along a line parallel to the j omega axis, but in the right half plane. Correct? You understand? So what do you think will happen if I take this loaf of bread and slice it further into the right? I mean, if the original response was like this, if I go further into the right half plane, what do you think is happening? So the rippling will reduce, and they probably do something like this. Okay. In the stop band, what do you expect to happen? Pretty much the same thing, correct? Because the distance from, if you go far away, the distance from some point on this line to each of these poles is virtually the same as the distance from a point on the j omega axis to each of these poles. Is this clear? Okay. So you can see that this finite gain can also be very easily explained by going through pretty much the same arguments as we went through for the parasitic pole yesterday. Okay. Now what do you think will happen if there is a parasitic pole as well as finite DC gain? If there is a finite DC gain, you would evaluate it on the right side on this red line. If there was only a parasitic pole, you would have evaluated it like this on this curve, Okay. Now if there is finite gain and parasitic pole, what do you think you will do? So you have to move this parabola like this. You understand? Okay. So what does somebody's do somebody's eyes light up now suddenly on seeing this? Okay, what I mean, the ideal filter response is to be evaluated on the j omega axis. Now if they are both parasitic poles as well as finite gain, we see that you have evaluated on this blue curve, right? This is the j omega axis. This is the origin, right? So this is the j omega axis. This is the sigma, okay. And so what, depending on the parasitic pole and the finite gain, it seems like there is one point here where the response due to the response of the non-ideal filter is the same as the response of the ideal filter. This is correct? Okay. And therefore, what must be happening at that particular frequency? The non-ideality due to finite gain is compensated by parasitic pole. Okay. So what is the parasitic pole doing? It is giving you excess phase at 90 at the unity gain frequency. Correct? Okay. Now if you have finite gain, therefore if it is compensating, what should it be doing? In other words, excess pole adds phase lag. So finite gain is adding phase lead. Okay. So you can also kind of understand that through this. What is the unity gain frequency approximately? Gm by C again, correct? But you can see that this is a first order filter, the denominator. So its phase can never reach minus 90. It will only asymptotically reach minus 90 at infinite frequency, correct? So at the unity gain frequency, its phase lag must be less than 90 degrees in magnitude, correct? So in other words, the excess phase is negative. In other words, there is a phase lead with respect to the ideal integrator phase. Does it make sense? Okay. So the moral of the story therefore is that the integrator has phase lead with respect to, all this is with respect to minus pi by 2. Okay. Then what will you see in the response? Yes. Yes. So you will see Q will decrease. So you will see a drooping response, or Q will decrease. On the other hand, if you have phase lag respect to minus pi by 2, you will have a peaking response, or Q will increase. Okay. Does it make sense? Okay. And if the phase is 90 degrees, then you will have, what do you call, the Q you realize will be the ideal. Okay. So some people try to attempt to make, so you can see that you can kind of what do you call, increase the or mitigate the effect of parasitic pole by deliberately reducing the gain of the integrators. It's not a very robust thing because the DC gain depends on Gm and R naught, right? Whereas the excess phase will depend on something else. So it becomes very difficult to cancel this across over all over time and temperature variations and all this stuff. Okay, but this is just something to be aware of. And intuitively this makes sense because if you had parasitic pole which causes excess phase, the quality factor goes up, right? If you want to bring the quality factor down, what must you do? You must increase the damping, which is equivalent to putting resistors everywhere, right, in parallel with the capacitors, so that the quality factor comes down. And you can see that at some frequency you will get the same response as the ideal. So by properly choosing the gain and the parasitic pole, you'll be able to bring this intersection to around the passband edge, in which case you will get what he calls the ideal response at the passband edge. But as I just told you, it's not a robust technique. Okay, so this completes all that I had to say on what you call block level aspects of transconductor capacitor filters. Okay, let us starting what you call Monday, we'll attempt to start looking at transistor based realizations of transconductors. Okay, by that time hopefully you would have completed your fourth assignment. It's due tomorrow, is it? Yeah. So the motivation for using fully differential filters will become apparent after you complete this assignment. And then Monday we start with transconductor realization. Okay.